Hi, this is Dave Nguyen, CEO and co-founder of Brain Scanology and the inventor of the LCPC transform. So in this presentation, we did a pilot study on measuring the shape of Hill-Sachs lesions in the shoulder. And we did this to show the efficacy of measuring shape via the LCPC compared to current approaches. I'd like to highlight that our technology is applicable to X-rays, MRIs, and CT scans because we measure structure and not intensity. So here is an example of a Hill-Sachs lesions resulting from dislocation of the shoulder. I went into the literature to look at the various shapes of Hill-Sachs lesions and then created a number of phantom lesions in order to provide proof of concept. So here are a series of Hill-Sachs lesions, the arrows pointing to the lesions to varying degrees of severity. I then also created phantoms of normal shoulders because I wanted to derive a metric that works on both normal shoulders and affected shoulders. And according to the literature, or at least in my observations, there seems to be at least two general morphologies of normal shoulders. Here I've defined the top one as the cliff morphology. That is, here's the cliff shape on the lateral edge of this right humeral head. And then the bulbous morphology, that is the morphology that looks like a light bulb. So first, I want to apply the 360-degree radial grid system to quantify these shapes. And before we do that, we have to find an objective way to define the center of that radial grid in every shoulder for both the normal cases and those affected by the lesions. In order to do that, what I did was I defined the midline of the humeral shaft that runs all the way to the tip of the head of the humerus. And that line, I then found the surgical neckline that's perpendicular to the midline. And then the midpoint of this red line here, defined by these two lines, is the center of the radial grid. And this way we can objectively identify a center location for every shoulder, whether it's affected by a lesion or not. As a brief explanation of how the LCPC works, the centroid, or it's not the centroid in this case, just the center point that we define serves as the center of the radial grid. The radial lines are spaced every 5 degrees, which allows us to calculate the distance of every intersection between the radial line and the blue line, which is the outer edge of the shape. That calculation looks like this in step 3. Right, step 3, we just linearized it right into step 4. And here we applied the fast Fourier transform to the data in step 4 to derive a frequency plot that represents the original shape that we started with. And what we did was we summed, in order to turn this frequency plot into a scalar value, we summed all the bins, all the bars, to produce one value that represents the shape we began with. This method allowed us to stratify normal shoulders compared to those affected by Hill-Sachs lesions. And if you look here on the right, there's a nice separation between the blue box here, which is the bulbous morphology, compared to the gray box, which are the Hill-Sachs lesions. But there is very poor separation between the orange box, that is the normal cliff morphology, versus Hill-Sachs lesions. And so we need to do better in order to separate what we know is normal versus what is a lesion. In order to do that, we use a different approach, that is this time a parallel grid system instead of the radial grid system. And the parallel grid system works as such. If you have a shape of interest you want to measure, you define a baseline from which the grid lines will extend perpendicularly. And then you can measure the distance of every intersection of the radial lines and the shape line, to the baseline. This allows you to generate a plot, as in step 4, to which you can apply the fast Fourier transform and get the frequency result in step 5, which represents the shape you began with. But before we did that, we again needed an objective way to define the surface we want to measure in every single patient. To do that, again, we use the concept of the midline of the humeral shaft, and its perpendicular intersection with the surgical neckline. As you see in step 2, the orange and red lines determine the endpoints of the shape of interest, this lateral face of the right shoulder, and that the green line, right, can serve as the baseline for our radial grid system. So this method here allows us to objectively extract the same lateral surface of every single patient. Once we did this, okay, we got very interesting results. First, let me remind you that previously with the radial grid system, we had a very poor separation between the normal cliff morphology and Hill-Sachs lesions. But when we applied this radial grid method, as seen on the left, we see a very robust separation, okay, between Hill-Sachs lesions and both the normal cliff morphology and the normal bulbous morphology. And here, in this case, right, it's just the one bin, right, the frequency bin number 4 that distinctly captures the difference between the bulbous morphology, the cliff morphology, and Hill-Sachs lesions, right? And this slide goes to highlight the versatility that the LCPC transform provides for clinicians, because it allows the clinician to define exactly what you're measuring, how you're measuring, and why you're measuring it, which are advantages that current deep learning methods don't provide. Furthermore, unlike deep learning methods that aren't interpretable, our approach allows the clinician to know ahead of time exactly what they're measuring and why they're measuring it. So whatever differences result, those differences are very interpretable. Next, I wanted to compare the efficacy of the LCPC transform to current methods. So current methods that clinicians use to assess Hill-Sachs lesions involve measuring the width and the depth of the lesion. And I want to show that the LCPC can measure things that depth and width simply cannot see. So I created a phantom, or 3 phantom lesions that have the same width, that is here this line in red, and the same depth, that is this line in green. And to show that, these 3 lesions, though it's visually obvious to the human eye where the deepest trough is, methods that rely on width and depth cannot distinguish between these 3 themes. So I created a new system to objectively measure Hill-Sachs lesions in this manner. And that is, first you find the line that intersects the 2 peaks that define the edge of the lesion. You then, in every patient, move this line in the same distance, that say 1 centimeter towards the middle of the humeral head. And that new line, that still has to be parallel to the original line, that new line serves as the baseline of the parallel grid system, which we have previously discussed, as you can see in step 3 and step 4, resulting in the frequency plot that represents the original shape. This method allowed us to quantify precisely, right, these 3 shapes. On the left here, this graph is, if you sum all the bins in each frequency plot, you can see that there's a robust difference between themes 1 and themes 2, but 2 and 3 are not well separated. But if you look at the individual frequency bins, you will find that particular bins capture the location of the deepest trough. Here in theme A, the deepest trough is on the left. And as you can see in the graph here for theme A, right, this set of frequency bins, right, shows the largest value when summed together. The same for theme B in the middle. As you see the graph here, theme B, the largest bar is in the middle. And in theme C, the deepest trough is towards the right, and that is captured in the graph below it. Right. Again, this goes to show the depth of information that the LCPC transform, right, can extract, especially compared to current methods that rely on depth and width. We can do the exact same analysis here, right, for other themes, such as here, this hypothetical scale of concavity. We can precisely measure every single shape in this gradation. We can do the same for this hypothetical scale of serration, right, going from left to right here, more and more jagged. And lastly, I just want to point out that since clinicians also view Hill-Sachs lesions in the axial plane in MR and CT images, right, we can also measure the shape of Hill-Sachs lesions and the humeral head, right, in the axial view. If you're interested, you can see our video in which we applied this technique to measuring the shape of rocks And as you can see here, the shape of these rocks are similar to the shape of the humeral head in the axial view. And in this video, you can see it on our website, particularly the page for use cases, and see how well we can, or how precisely we can measure each distinct shape. So in conclusion, the LCPC transform, one, provides the flexibility of capturing biological information that is inaccessible to deep learning methods. But the cool thing is that once you have defined a way to objectively measure what you want to measure, then you can employ the deep learning approach to quickly identify the shapes for you. Secondly, LCPC transform, what it does is it boosts the diagnostic intuition of the clinician, because it translates the hallmark clinical features into exquisitely precise numbers, much more precise than current methods allow. And lastly, whatever we can measure, right, consistently, we can develop a machine learning model to predict. The information that we extract from the LCPC transform can develop machine learning models that that can do things that area and volume simply cannot.